Alright guys, welcome to Rational Exponents. So what you're going to have to know today, the essential understanding will be that you can write a radical expression in equivalent form using fractional exponent, rational exponents, okay, instead of radical signs. So we might be given a radical problem, and then we're going to change that to exponential to help us actually simplify some of these problems. So what this essential understanding is actually telling you is that if you have the nth root of x, that's the same as x to the 1 divided by n. So n, whatever the index is, becomes the denominator, and whatever the power is on x becomes the numerator. And this works for any positive integer n. Radical form equals the principal root. So the other thing, when we get that, the radical form here would equal the principal root like before, the value that would be given on the calculator. A couple other things to know: when you have n, the nth root of x to the n equals n over n, and we'll talk about this later, especially this second part, the absolute value of x if n is even. So this is something we have to pay attention to a little while. We'll actually go back and redefine this later. So if this part is unclear, we'll clear that up for you when we get to an example that involves that. Alright, so we're going to get right into simplifying, and so the first two examples here are just trying to get you to write in equivalent forms. So in part A, we're going to write x to the 1/6 power in radical form. So we actually want that in square, some type of root. So we have x to the 1/6. So the denominator is the index, so it's the 6th root of x to the first power. Remember, x will have the power of whatever that numerator is. And this is just by definition. That's that first part there, the essential understanding. In number 2, we're going to go backwards. We're going to start with the radical, and then we're going to put this in exponential form. So we have the 4th root of z to the 1st. So the 4th root of z to the 1st is equal to z to the 1/4 power. The last two examples here is if we simplify numbers. So we have 216 to the 1/3 power. Now you could plug that into your calculator and get the answer, but let's rewrite this. Well, 216 to the 1/3 power is the same as the cube root of 216. Now 216 is a perfect cube. It's 6 cubed. So I rewrite 216 as 6 cubed to have indexes match, and that answer is going to be 6. Okay, so in this case n was not even, so I wouldn't need the absolute value bars. Here in part D, 7 to the 1/2 times 7 to the 1/2. Two numbers with the same base, you can add exponents, so 1/2 plus 1/2 would be 1. So this will be 7 to the 1st. But you can always rewrite this as the square root of 7 times the square root of 7 equals the square root of 49, because you can multiply these numbers together because they have the same index. Square root of 49 is 7, and that's again the principal root. So this is just in purple here using the definition. There's other ways you can get there, but we were using the definition. In the next two examples, we're going to continue that idea of simplifying numbers and variables together. We're going to evaluate each expression, and so let's simplify what we have here. In part A, you have 81 to the negative 1/4 power. Now, before we can do anything, our index has to be positive. And so what we're going to do is we're actually going to get rid of the negative power. So we're going to write 81 to the negative 1/4 as 1 over 81 to the 1/4, and then we're going to simplify from there using the essential understanding, using what we know, equivalent forms of radicals and exponentials. So in the step here, I write 1 over the 4th root of 81. So now I've simplified that power, that exponential, into radical form. Anytime you have a number under a radical, you want to try to make that number underneath match the index if possible, like prime factorization. 81 is actually the 3 to the 4th power, so here in this next line I write 1 over the 4th root of 3 to the 4. That means the 3 comes out, so it's 1 divided by 3. So the answer is 1/3. Okay, so be careful, some people would write 3, but don't forget the 3's in the denominator. In part B, you have the 4th root of 5 times the 4th root of 125. Both indexes are the same, so you can combine the numbers underneath, but watch what I've done first. I left a 5, and we know that 125 is 5 cubed. So I rewrote that here. Now, we can multiply those together, and we get 5 to the 4th. Well, now you have 4th root of 5 to the 4th, which is 5. So the answer there is 5. And notice how 125, 5 cubed, that didn't help me with that index of 4, but I knew I could multiply. Okay? Key concept here, and we're pretty much really have done this. If the nth root of a is a real number, m is an integer, and m over n is the lowest in terms, then a to the 1 over n equals the nth root of a. If m is less than 0 and a can be 0, a to the m over n equals the nth root of a to the m can be written in this form. So we've actually applied both these rules, but the second one, take note that if you have the nth root of a to the m, that m can actually go on the outside. That's what they're telling you. It's a very subtle change there. So let's look at an example. What are x to the 3/7 and y to the -3/5 in radical form? X to the 3/7 is like we've been following, so this first definition really isn't anything new. It's going to be the 7th root of x cubed. The only difference here is that really our numerator had changed, whereas we'd have a 1 here, now we have a 3x cubed. Okay, so that's the 7th root of x cubed, or using the second definition here, that becomes the 7th root of x, that whole thing cubed. So these are equivalent. When you have y equals -3.5, y to the -3.5, I write 1 over y to the 3.5, excuse me. And we do that first because we get rid of the negative. 3.5 is 7/2, so I really have y over 7/2, which simplifies to be the square root of y to the 7th. Now the number inside is larger than 2, so I can simplify to being y to the 1 over y cubed to the times the square root of y. The fourth frame, we just have 3 examples left. Simplify each of these expressions. And so what we're going to do here, in part A, we have the 4th root of 27 over the square root of 3. Now, normally you might say, well, let's just write this over one radical. But we can't because the indexes don't match. So you have to be careful. The indexes don't match, so I can't write this fraction under one root. I can, however, change those into equivalent forms, and I do. I write them in exponential form. That's what you see in step 2 here. 27 to the 1/4, 3 to the 1/2. Now, I still can't divide these out because they're not the same base. So again, be careful. But 27 is 3 cubed. So notice in the next line, I have 3 cubed to the 1/4 over 3 to the 1/2. Okay? A power to a power, you multiply, you get 3 to the 3/4 divided by 3 to the 1/2. And now I can subtract powers. 3/4 minus 2/4 is 1/4. So you get 3 to the 1/4 or the 4th root of 3. In part B, I have the cube root of 64z to the 6. So first step, I write this in exponential form. That's to the 1/3 power. Then I simplify inside. 64 is 8 squared. Z to the 6 I leave to the 1/3 power. I distribute the 1/3 and I get 8 to the 2/3, which when you simplify is 4. And Z to the 6 over 3, which is 2. So 4z squared is my final answer there. Now, in the last example, we're going to have, this is more complicated, it's a fraction, x to the 1/2 minus 2 over 3x to the 1/2 plus 2. So what you're actually going to do is you're going to multiply by the conjugates, which what should I do here? Okay, and then I put the box method over here so you can see the work I'm doing in order to get to this next line right here. That's a little more tricky. So there's the work for the box method to get to this step. And then you have 3x to the 1/2 times 3x to the 1/2, which is 9x to the 2 over 2, which is just 9x. And then 2 times -2 is minus 4. These are conjugates, so the middle term is going to cancel out. Basically, you're just squaring this term and squaring the -2 here to get this bottom result. 3x to the 2 over 2 is just 1, right? 2 over 2 is 1, so you get 3x to the first power minus 8x to the 1/2 plus 4 over 9x minus 4. So that's using rational exponents. We didn't really get to, and I said we were going to get to the example where we covered that absolute value, but that actually comes in a later lesson. I apologize. If you guys have any questions or comments, you can type them below, or you can email me at nicholas.bennett@dc.gov, and we'll see you next time.